theorem for derivatives states that given a continuous differentiable function f and x values a and b, there exists at least one x value c between a and b such that f prime of c is equal to the slope of the line secant through f of a and f of b. Here's my function f. As you can see, it's a cubic equation with real coefficients, so we know it's both continuous and differentiable. F is built from these sliders over here, which we can use to change its shape without too much hassle. Now we need our x values a and b, and the secant line that goes through f of a and f of b. This point D is a movable test value we use to look at the direction the function is moving around given x values. As we can see at certain points, such as here and here, the function is moving sort of parallel to the orange secant line. We don't know exactly what those x values are until we have a derivative. I built and graphed f prime here. We're looking for a c such that f prime of c equals the slope of the secant line. If we were to subtract the equation of the secant line from f and then take the derivative, it would be the same as subtracting the slope of the line from f prime, which would yield a quadratic equation equal to 0. Easy enough for us to solve. But what would that look like? Well, here I've graphed the first half of that. F minus the equation of the secant line and reflected across A for visibility. As you can see, the places where f of d seems to be moving parallel to the orange secant line are potential candidates for c, correspond to maxes and mins on our transformed f. Now that we have a good idea of what we're looking for, we should go ahead and solve for and graph c. Since the derivative is a quadratic, we get two values for c. You can see that we can move either a or b, or modify the original function. These each change the values that we get for c. But no matter what happens, f prime of either c is equal to the slope of the secant line.